I would. Shut up. I would.
Okay. Scoreboard, buddy. Scoreboard. Okay. So here's the next part of the story. We're back to Luke being in orbit 174 kilometers above the Earth. We just established that the centripetal force equals this gravitational force. Now, what I want to find out next is how long it's going to take Luke to orbit. Okay? So, we're going to start off with the idea that the mass of Luke times the centripetal acceleration is going to equal big G, mass of the Luke, mass of the Earth over r squared. Now, what's the way to calculate centripetal acceleration that involves radius and period? What'd you say? 4 pi squared r over t squared. Again, nothing personal, Luke. What are you going to do?
I go by pi.
You drop out of the equation. Okay? So Luke's gone. Now, this becomes the pirate's favorite equation because we're going to cross multiply. So I'm going to get 4 pi squared r cubed. Okay? This is a pirate's favorite equation right here because you have r cubed. And that's going to equal big G mass of the Earth t squared. Now, one thing I want you to keep track of. We're working this with Earth at the center of the orbit. It doesn't have to be Earth. It could be the sun, it could be the moon, it could be Jupiter. Okay? It's just whatever's at the center of the orbit. So, this is what I call like the Swiss Army knife equation of planetary motion. Because what's the Swiss Army knife known for? Gadgets, right? It does everything. Tweezers, a knife, a corkscrew, a particle accelerator, whatever. Okay? It's got it all. So the cool part of this equation is that it has 3 different variables in it. It has radius, the mass of whatever you're orbiting, and orbital period. So let's say, for example, you're tasked with finding the mass of the Earth. We have lost all data. The internet's down, we have no data. We need to find the mass of the Earth. Well, conveniently, we have a moon that orbits us, right? So if we need to find the mass of the Earth, we know the orbital period of the moon is about 30 days. Okay, about every 30 days you get a full moon. Okay, so orbital period is about 30 days. So if we have any kind of rough idea of the distance from the Earth to the moon, we can solve this for the mass of the Earth. And that's how we find like the mass of Jupiter, the mass of Saturn. Any planet that has a moon that orbits it, if you can look and see the orbital radius of that moon and the orbital period of that moon, you can solve for whatever the mass is at the middle. Now, one of the calculations you're going to do in your homework today, your phone and your maps app works off of geopositioning satellites, okay? And these satellites, GPS satellites, are parked in an orbit above the Earth. Now, what you're going to see is that Luke is going to orbit about every hour and a half, okay, at the altitude that he's at. Geosynchronous orbits have an orbital period of 24 hours. So what that means is that we could, if we wanted Luke to always be above us, we would park Luke in an orbit where the period of Luke's orbit is 24 hours. So what that would mean is that the Earth spins once on its axis, Luke would go around 24 hours. So he would always be above the same point on the Earth all the time. So if I knew the period, I could solve for radius. So what you need to be able to do is take this equation and solve it for any variable. Radius, mass, period. But again, this is the quintessential MKS system. This period has to be in seconds. What are the odds that I give you the orbital period in seconds?
Slim.
0. Okay? 0. I'm going to give you that orbital period in days, hours, something like that. Okay? This radius has to be in what units? Measured from the
Center of the earth.
center of the earth. Okay? Pay attention to that part of it. All right, so let's start with this. Sydney, I want to solve this equation for t. So what are you going to get?
4 pi squared on the third over g and e,
Big G, mass of the earth, and then what?
a square root.
Square root of all of that. Now, sometimes you'll see this written, because what's the square root of 4 pi squared? 2 pi. So sometimes you'll see this written as 2 pi times the square root of r cubed over big G, mass of the earth. Now, if you really wanted to get fancy, in case you haven't noticed, here's the trend. Almost all of these equations involve big G multiplied by the mass of the earth. Okay? So if you really wanted to get efficient and get nerdy, you could take big G times the mass of the earth and store that as another variable. So then you wouldn't even have to type in G times M. Okay? You could just recall that. Okay? It's hardcore, but I'm just saying. Now, if you really wanted to go hardcore, in terms of if you were, legitimately, if you are a satellite engineer and you're using this equation a lot, mathematically, can I do this? Can I take 2 pi times the square root of 1 over big G, mass of the earth, times the square root of r cubed? Can I do what I just did? Mathematically, is that legal? Chuck? Legal or not legal?
I think so.
Yeah, it is. I just pulled that out from underneath the radical. So if you wanted to, if you were doing this equation a lot, you could take the square root of 1 over big G mass of the earth, because that number is not going to change as long as you're orbiting the earth. 2 pi is not going to change. So this is actually, mathematically, t equals some constant times the square root of r cubed. Okay? That's what it is. That's it. That's it. That's the number. It's just some constant. Now, before you touch a calculator, okay, before you touch a calculator, we're going to do this with Luke. So I've got 2 pi, and that his radius was 6.5. What was it? 6 point what? When we added the 174,000 to the radius of the earth.
6.5453.
5453. And that's going to get cubed, divided by 6.67 times 10 to the minus 11 times 5.979 times 10 to the 24th kilograms. Step away from the calculator. Step away from the calculator. Connor S. I take 10 to the 6th and I cube it. What am I going to get?
10 to 18.
10 to the 18th. I got 10 to the 11th times 10, 10 to the negative 11th, times 10 to the 24th gets me 10 to the,
13.
which gets me 10 to the,
Yeah.
but then I got to take the square root of that and I got to multiply by 2 pi. So trust me on this one, this is also going to work out to be 10 to the 3rd, okay, in seconds. So here's the beauty of this. Anything in near Earth orbit, whether it's the moon, the earth, doesn't make any difference. Orbital periods are going to be 10 to the 3rd. Velocities are going to be 10 to the 3rd. You don't have to remember different exponents. Period is this number and velocity is that number. Okay? They're both 10 to the 3rd. Okay? They're both 10 to the 3rd. Now, here's what you're going to do wrong. You're going to forget to square or cube the radius. Then you're going to get done, and you're going to forget to take the square root. Trust me. But this is the beauty of this. Your orbital period is 10 to the 3rd. Your velocity is 10 to the 3rd. It's a simple number to remember. Now, somebody chuck that into your calculator and give me the exact answer.
3.37E3.
What'd you get?
3.37.
Nope, we have discrepancies already.
5,260, or
5 point what?
5.27 times 10 to the third.
Times 10 to the
Third.
seconds,
Yep.
okay? If you cannot get this on your calculator, this is the time to figure this out, okay? Now, out of curiosity, divide that by 60, Chuck.
87.8.
87.8 minutes, which is about an every hour and a half, okay? So what that means is if Luke was in orbit, he's going much faster than the Earth is spinning, okay? He's in orbit. So if you like sunrises, go and orbit the Earth. You're going to get a sunrise about every hour and a half because you're going to complete one orbit around the Earth every hour and a half. If you like sunsets, oh, I'm going to get one of those about every hour and a half. Now the problem is that completely jacks up your circadian rhythm because, oh, you're used to one sunset and one sunrise about 12 hours apart, roughly, okay? Imagine that happening every hour and a half. Like, oh, time to wake up. Oh, time to go to bed. Oh, time to wake up. Oh, time to go to bed. Okay? That's what, there's any number of things that you get messed with when you're in space for a long time. So, here's the story. If we boost Luke into a higher orbit, what's going to happen to the value of t? It's going to become larger, okay? And you have two things that are happening. So if you look at a graph of orbital period, and this is radius, and we're going to start right here with the radius of the Earth, okay? Because you can't obviously orbit inside the Earth. So as you go further and further from the radius of the Earth, what's this graph going to look like? Andrew?
It's going to curve up.
Yeah, because the farther you get from the Earth, what's going to happen to the period? It's going to take longer. Now, if you were to plot velocity versus period, here's the radius of the Earth, what would that velocity graph look like, Scooter?
Like shallower.
But what would it still be that same shape?
No. Yeah, absolutely. Just pick one. Yes, it would be.
Oh,
Oh, okay.
here's the reason why. If you look at velocity, which is big G M over R, period is 2 pi r cubed over big G M. If you make the radius bigger, what's going to happen to your velocity?
It's more.
So that graph is going to go like that. So hopefully that makes sense. So when we boost Luke into a higher orbit, there's two reasons that that period is going to take longer. Number one, he has a greater distance to travel. Okay? He's got to go, it's going to take him longer to go around. Situation number two, not only does he have a greater distance to travel, what happens to his velocity? It becomes smaller. Okay? So you got a longer distance, but you're going slower. So you have two things that contribute to make that orbital period longer. Okay, got that. Cool. Okay, so let me hand out the assignment.
I'm going to go to the restroom now.
Oh, that's us.
Okay.